Okay, so in this section, I'm going to talk about Theorem 12.2 from the textbook, which is basically just a result about certain quantities that we can use to kind of measure the extent of exponential growth or decay that occurs in a sequence in sort of a vague sense, okay? So let me just write the theorem statement. So this is Theorem 12.2. Let Sn be any sequence of non-zero numbers, then we have lim inf of Sn plus 1 over Sn less than or equal to lim inf of Sn to the 1 over n, which is less than or equal to lim sup of Sn to the 1 over n, which is less than or equal to lim sup Sn plus 1 over Sn. Okay, so let me talk a bit about where this comes from, because it probably doesn't seem obvious at all when you first look at it why this would be the case. Well, first of all, I want you to imagine what these things represent when the sequence, so imagine if, Sn equals a to the n for some, real number, non-zero real number a. So for a non-zero, right? Then Sn plus 1 over Sn is the absolute value of a for every n. So this is just a, and then Sn to the 1 over n, obviously absolute value is also absolute value of a. So this is just absolute value of a. This is absolute value of a. This is absolute value of a. They're all absolute value of a, right? So these sequences, or these like the lim inf and lim sup here, they are kind of telling us what the base of the exponential would be for an exponential sequence. Now, of course, there are many sequences which either mimic exponential behavior, but not exactly. If you just sort of fudge the numbers a little bit, you'll get a sequence which is not exactly exponential. And but these numbers can still tell you something about, roughly how fast it would be growing or decaying. Or, if a sequence grows faster than an exponential sequence asymptotically, like take n factorial, for instance, right? If Sn was n factorial, then this would be like n. This would be, the nth root of n factorial, which we don't actually have a good way. Well, that you can figure out what happens to that. I'm not going to get into it right now. But like this is n, and this is n. So these obviously go to infinity, right? So these should all be infinity, basically, right? Is what's happening here for something like n factorial. That's because n factorial grows like infinitely faster than any exponential function, right? Or if you had something like Sn equals n squared or something like that, then you'd have like n plus 1 squared over n squared, and this would approach 1, and this would approach 1, right? So that would be saying that like there's no real detectable exponential behavior in a function like n squared. So these are commonly used to kind of like detect exponential behavior in a sequence. And what this is saying is that basically these sort of successive differences between the terms, the successive quotients here, are basically more sort of widely varied, and they're more erratic than if you take the nth root of each term. So let me kind of explain why that should be like an intuitively, not obvious, but like an intuitive idea, okay? So I'm actually just gonna go to a new page here. So why do we expect theorem 12.2 to be true? Okay, so consider the related chain of inequalities, which I'm not going to prove, but I believe this should be true. So lim inf Sn plus 1 minus Sn. Let's say absolute value. Why not? Not that it really matters, I don't think. But this would be less than or equal to the lim inf, or yeah, lim inf of Sn over n less than or equal to lim sup of Sn over n less than or equal to lim sup of Sn plus 1 minus Sn, right? So you can think about these as like, you know, successive differences, right? So this is the difference from one term to the next. This is the number you would have to add to a term to get to the next term, right? Number you add to get to the next term, right? If you think about it that way, right, let's call that, call it delta n, right? Then if you think about this number here, right, this is just a term here, which is actually, in terms of these delta n's, this would be the sum of the first n of those, right? So what we're looking at is something like lim inf of, so and I'll explain, you know, why I changed everything to be, differences here and like a quotient here, difference here, right? Instead of the quotient, exponent, quotient. I'll get to that in a second. But let's just consider these inequalities here, right? So lim of this sequence of delta n's, right, is less than or equal to the lim inf of delta 1 plus delta 2 delta 1 plus delta 2 plus delta n, plus delta n over n, which is less than or equal to the lim sup delta n, right? So now, if we look at it this way, if we look at it in terms of these deltas, right, the difference from one term to the next, what we're saying is that if you just take the sequence of delta n's, you know, it could be doing whatever, right? I mean, it could go up, it could go down, like who knows what it's doing. But if you start taking a running average of the delta n's, right, then by taking the average here, you kind of like smooth out the sequence of delta n's. When you take a running average, then it's kind of like you're ignoring the individual differences between them, and you're trying to figure out just what they look like overall, right? What do the delta n's kind of look like overall, right? So it should sort of make intuitive sense that if you have like a collection of data, right, then the average of those data should kind of be somewhere in between the two extremes of how that data behaves, right? That's the sort of moral. So the moral, right, is the average lies between extremes, right? So, okay, now the question is, why is this related to, so why is, lim inf Sn minus, or Sn plus 1 minus Sn related, and the lim inf or sup, actually, right? And then the lim inf or sup of Sn over n related to 12.2, right? The statement of 12.2, which involved quotients. Given Sn with Sn not equal to 0, we could define Tn by Tn equals the log. Okay, and I know we haven't defined the logarithm, okay, but I mean, obviously the logarithm still exists, it's out there, right? So I'm just using the logarithm right now as a way of quantitatively analyzing the relationship between the sequence of, like, you know, differences and averages versus the sequence of quotients and nth roots and stuff like that, right? So I'm just trying to use the logarithm to illustrate to you why these, like, two concepts are related in reality. Not how we can justify, not how we can prove. We're not going to prove the theorem using the logarithm because we haven't defined it. Okay, but if you take Tn to be the logarithm of Sn, the absolute value of Sn, right? Then the statement of 12.2 is equivalent to the statement that the lim inf of Tn plus 1 minus Tn is less than or equal to the lim inf of Tn over n less than or equal to the lim sup of Tn over n less than or equal to the lim sup of Tn plus 1 minus Tn. Okay? So basically, what I'm saying is that Sn plus 1 over Sn is the multiplicative you know, the multiplicative difference, or geometric difference if you want. Actually, yeah, that's better. Let's say, or yeah, actually, yeah. So let me just, or geometric. We often use geometric to refer to multiplicative or exponential phenomena in math. And Sn to the 1 over n is the geometric mean of these differences. Okay, so it's basically taking the nth root here is equivalent to, is sort of like taking an average, but in, you know, taking an average in a geometric sense. This is actually, the geometric mean is a concept that actually is talked about in math. It has a formal definition where the geometric mean of a collection of numbers is the nth root of the product of all of those numbers, right? So in this case, what I'm saying is, you know, Sn to the 1 over n is the nth root of S2 over S1, S3 over S2, and so on. At least if you ignore, okay, there's also an S1 in here. Whoops. Let me kind of, so we have an S1, S2 over S1, S3 over S2, and so on, all the way up until Sn over Sn minus 1, right? So if you multiply all those numbers, you literally just get Sn, right? But this, when you write it this way, this is looking at it as an average of all of these different, of all of these numbers, basically, okay? So that is, and the sort of relationship that shows you that this really acts like an average is using the logarithm here, where you can sort of relate it to the logarithm sequence. And then with the logarithm sequence, these literally do become differences, and this literally does become an average. It becomes the average of all of these differences, okay? So that's kind of intuitively why we expect this to be true. Okay, so now let's prove it. So I'm actually going to erase a lot of this to make room. Okay, so let's prove this. And remember, Sn is just an arbitrary sequence of non-zero numbers. Now, this inequality is obvious, right? Because the lim inf of any sequence is automatically less than or equal to the lim sup of that sequence. And then the first inequality here is similar to the third inequality. Okay, so we're going to focus on this one. So we're going to prove this one. Okay, so let's write. I'll try to use the book's notation here. So lim sup Sn. Oh, sorry, this should be outside of the absolute values here. So lim sup Sn to the 1 over n. We're going to call that A, I believe. Let me make sure. Oh, alpha, sorry. So let's call this alpha. And the lim sup of Sn plus 1 over Sn, we're going to call L. Okay? So we're going to assume L is less than infinity, right? Because obviously if L is infinity, then this inequality is just trivial because anything is less than or equal to infinity, right? So we're going to assume L is less than infinity, is less than infinity, right? And our strategy will be to show, so we want to show that alpha is less than or equal to L1 for all L1 greater than L. Okay? So remember, we've actually seen this strategy before once already, right? And I tried to explain it before, and hopefully that sunk in a bit, but if you show that alpha is less than or equal to L1 for every number L1 bigger than L, that shows that alpha is less than or equal to L itself, right? Because if alpha was greater than L, then you'd be able to find a value of L1 in between L and alpha, right? And then this statement would not be true, right? So alpha cannot be greater than L if this is true. So it's enough to show that alpha is less than or equal to L1 for every L1 greater than L. That's what we're going to do, okay? So here's how we do it. So since lim sup Sn plus 1 over Sn equals L, which is less than L1, right? We can find a capital N such that the supremum, remember, so I'll explain this in a sec, but the supremum of all of these numbers for n greater than capital N is less than L1, right? Because remember, so this supremum here is just like one of the terms in the sequence that defines the lim sup, right? This is like Vn, right? So remember, like the lim sup is just the limit of this sequence of Vn's where you let this number n increase. So, if L1 is bigger than L, L is the limit of the Vn's, right? If L1 is bigger than L, then the Vn's eventually have to get smaller than L1 in order to approach L, right? That's all we're saying here. So, so that means that, right, for this value of n, Sn plus 1 over Sn, absolute value is less than, let's say less than L1, yes, because this is less than L1 for all n greater than capital N, right? Because the sup of those things is less than L1, then the individual numbers themselves are also less than L1, right? Okay, so remember the overall strategy here is like, we're gonna try to take advantage of the fact that we're thinking of Sn to the 1 over n as the average of these numbers of the first, several of these numbers, basically. So, okay. So all we want to do is just show that like the average has to be less than or equal to, right? If all of these things are less than or equal to L1, then their average should be, less than or equal to L1, basically. Okay. So let's see, right? So for n greater than n, that's sort of the motivation for why we make this following, why we write this following equation. So we have Sn equals, right, Sn over Sn minus 1, Sn minus 1 over Sn minus 2, and so on to Sn plus 1 over Sn times absolute value of Sn itself, right? So again, this whole expression here is literally motivated by what I was just saying before about thinking of this as basically, or thinking of the nth root of this as the average of all of these multiplicative differences between the successive terms. Okay, so this is basically, we're writing out how to get to Sn from S capital N by like multiplying by different factors, right? So, and then because each of these things is less than or equal to, is strictly less than L1, right? So this is less than L1 times, L1 times, et cetera, times L1 times Sn, which is L1 to the n minus n times Sn, right? So, right, then yes. So if we basically, right, okay. So this is equal to L1 to the n times A, where A is L1 to the minus capital N times absolute value of Sn. Okay, so the idea is all we're trying to do is just like isolate this exponential. This part like grows exponentially or grows or decays exponentially with little n, right? We just want to isolate the dependence here on little n. So we're grouping everything else into just a constant. And then if we just take the nth root, right? So then, Sn to the 1 over n is less than L1 to the times A to the 1 over n, right? For n greater than n. And then if we take the limit as n goes to, or not take the limit, sorry, but, so since A to the 1 over n goes to 1, then we see that, right, the lim sup of Sn to the 1 over n should be less than or equal to, oh, sorry, my tablet stopped working. So then the lim sup of Sn to the 1 over n is less than or equal to L1, right? Because basically this A1, like basically if you think of this as a sequence and take the lim sup on both sides, right? If we're just taking the lim sup on both sides of this inequality, this is a convergent sequence. We showed, or at least there was a theorem in section 9 which stated that this sequence converges to 1. So by the previous, by 12.1, right? By theorem 12.1, we know that we can take the lim sup on both sides, and the lim sup on this side is just going to be L1, right? And then so we end up with this lim sup of Sn to the 1 over n is less than or equal to L1, which is what we wanted to show, right? We wanted to show that alpha is less than or equal to L1. And of course, L1 was arbitrary. So L1 was arbitrary. So alpha is less than or equal to L. which is what we wanted. Okay, so yeah, again, this whole like trick here of doing this sort of telescoping, right? This is a telescoping expression because all the internal factors just cancel out with each other. This trick really comes from the motivation I was talking about of thinking of the nth root of Sn as the geometric average of the successive differences between the different terms. Okay, so that's all for this section. See you in the next one.